Okay, thank you, Professor Jiang. That's a very nice introduction. And hello, everyone. A very good morning. I think it's the great pleasure, to have the lecturer, between the two departments. I think the Seoul National University and National University of Singapore. And I know the colleague in they also working on like the title I'm going to present today, the energy storage. I know that's very excellent. The professors in the department. I think it's really a good opportunity, for us between the staff and the students, so we can stay together to have such the lecture. And the title said is large-scale electrochemical energy storage. I believe what's it about, right? So especially the energy storage, if you use an electrochemical cell, it's really in our daily life, every the corner to be used. I believe, most of the time the day you will bring 1 or 2 batteries to you. But here, what I'm going to present is slight different. It's for the larger scale application. It's not for the portable electronics. So I try to split my talk in a different sections. I think Professor Jiang previously suggests we try to give a more introductory the content so that people, the student have the background. So then I think the first half, so I've give, the overview, for the large scale energy storage technologies. And actually, so that's one of the modules. So we have in NUS, for the final year student and master students, we call this the materials for energy storage and conversion. There's one chapter, so there's a battery for the large scale energy storage. I think it's also the group opportunity to share, our lecture, the content, with the friends in Seoul. And my talk is going to have the 4 sessions. So the first, I will try to answer the question why we need a large scale energy storage. And the second, I will narrow down why particularly, so the electrochemical energy storage is more interesting, is more relevant, compared with other energy storage technologies. And then the main body of the talk is the introduction of a different large-scale electrochemical energy storage, the technologies. So the one that people developed in the past and the current use today, and the emerging the technology, some of we believe will be used in future. And lastly, so I will try to introduce some of our study it's been doing in Singapore. So that's the electrochemical energy storage system going beyond the electrolyte interface. I know that's 1.5 hours the talk, and I try to make a stop maybe after I finish the first 3. Okay, so then if you have any questions, I think we can also discuss during the break. Okay. Okay, so I move to the slides, try to answer why we need large-scale energy storage. And actually the slide I prepared recently, for the new module for our master students. So that's the thermodynamics for sustainability. I think it's relevant. I think nowadays sustainable development becomes so important, right? From the government, to the different sectors in our society. If you look at the definition of sustainability, itself is very clear. So it's a kind of societal goal. We aim for the humans to safely coexist on our planet Earth over a long time. Basically, what we are doing today is for our future generation. So whatever we have in a different area, we need to look at if it's sustainable, and especially so here. So there are the 3 important pillars when people talk about the sustainability. One is environmental, one is social, and one is economic. So you look at the national nation, they have the target. They have a 17 the global goals, by the 2030s. Involves the different aspects in a different area. But if you look at quite a number of them they associate, with the energy. Especially when you talk about the environment. So the energy is always, the keywords. And I think here is interesting, the graph I got from the textbook we use in the module. So that's the energy, the sources that people use in the old time, like from the Stone Age, all the way, to today. You look at the field from wood to coal, the oil, the natural gas, and today we have nuclear, and emerging, we use the hydrogen or the ammonia as the so-called clean fuels. So the development of energy sources, they follow the trend. It means the carbon, the hydrogen ratio, they're reducing, from wood, to the hydrogen, obviously. So the carbon content, we need to cut the carbon content in our fuel so that we know that's reduce the carbon emission, so that we can mitigate the global warming or the so-called greenhouse effect, right? So that's the very important target we need to achieve, by 2030 or by 2040, 2050. That's different the target. So that means the energy. So that's the very important the topic, in terms of the sustainability. Okay, and if you look at this year, so they have a report. It just a new release is for the World Energy Transition Outlook. The conclusion they got is we are not on track to limit warming to the 1.5 degrees. So that's so that's the target. So we set in the Paris some time ago. So the temperature goal. If the based on our current the activity, our current the practice. So we are not able to achieve such goal to limit the temperature increase by 1.5 degree. And so that means there's a bigger pressure, to further cut the carbon emission, especially, for the different energy sectors. So for example, we need to have 90% decarbonization in the 2050s. Of course, so this decarbonization can be achieved with different approaches. But today, I'm going to talk about, how the energy storage can contribute, to this goal. And further, to highlight the importance of the environmental or the sustainable development, here related to the climate change. So that's a book I think is published last. And he highlighted the technologies, a long list, the technologies needed if you want to avoid the disaster. So the different technologies here, for example, so we need have the hydrogen to produce without emitting carbon. So basically, so that's the so-called the green hydrogen to production. It's not from the steam reforming. We need to have a hydrogen produced, for example, from the sustainable renewable energy like solar or the wind can produce electricity, so then it can electrolyte the water, for the hydrogen generation. And also that's related to what I'm going to talk today. So that's a great scale electricity storage that can last for the full season. So that's for the long duration energy storage. Not for the portable electronics, it runs for a few hours. And so this, I think in the following slide, will give you a more specific example why we need a greater scale electricity storage. It's mainly because, so we have more and more the penetration of renewable energy, like a solar and a wind. And unfortunately, so this energy, the sources are not dispatchable. That means it's not predictable. So we need to store that when that's the surplus of this renewable energy that can use as a need. And also, like the fuels or the synthetic fuels or the synthetic natural gas. So this is also important, the direction related to the energy, the production with the method. And others like the zero, the carbon, the steel, or zero carbon, the fertilizers. The fertilizer today is mostly, from ammonia, from the Haber-Bosch. The method, the need to get hydrogen, from the natural gas, right? So it itself emits a lot of the carbon dioxide. So I will not, go through all the list. Because here, you want to avoid the climate disaster, I think the conclusion, from the book is electrification or the decarbonization. For the different sectors, especially they involve the energy use, we need to try to electrify it. And later I'll come back to this point why the electricity is so important in our society. And then we have this carbon-free or the carbon neutral, the process. And the relevant to the talk today, I gave it a different conclusion. We need a battery miracle, and we need a hydrogen miracle, and we need maybe a zero carbon miracle. And I just slightly modify, the words from the book, because later I'm going to touch on some topic in addition to the battery. Okay, so now let's look at why the electricity is so important. So there's different energy, the form, right, for our use, like thermal energy, like mechanical energy, or they have the photo energy or the chemical energy is different, the form. The electricity, we know, so that's the lifeblood of modern society. That's one of industrial revolutions we have. And electricity becomes a very essential part of our life. So you can look at the things around. I don't think we can, for a lot of us, cannot survive without electricity, especially in the hot summer time, right? So not only that lighting, the heating, cooling, like refrigeration or the different appliances, the computers, electronics. But what I'm going to discuss here, so why the electricity is a so important form for our use, especially in the context of energy storage. We can store energy in a different form, and in the end, we try to use the electricity, right? So so how or why we need to convert electricity in other forms. So that's will be an important part of today's the talk. Okay, so we comes to why the large-scale energy storage. In the previous slide, I mentioned the electricity, that's the critical. And is in a different the places, if you look at the graph as shown here, it's just like the city. And if you take Singapore as example, is a city-state. The whole country is just the city, and we have some remote islands. And if you look at the infrastructure, we have there's different sectors, the industry. The energy is the production and energy the use. So they're in a different. They're distributed in a different places, and especially, as I said, we want to decarbonize the use of energy. And important, so the renewable energy, especially the solar energy and the wind, become a very important part in our energy the mix. And so, as I said, so like solar energy is only available in the daytime, right? And when you use at night, you can imagine we have to have a means to store the energy, and not only the night time, even in the daytime, this energy resources are not the stable. So when the sunny, the weather maybe can generate more electricity, but the sunny have a cloud, so then we reduce the power greatly. So we need the means to store the energy, the produce electricity. And you look at the scale. This energy storage is not one we use in the portable electronics, or even is not in the electric vehicle. So here we are talking about the megawatts or even the gigawatts, the level, for the few hours or even the longer time storage. And for this, obviously, we need different technologies which is suitable, for such the applications. And to give you the more the specific example, why we need the large-scale energy storage. So here there's the scenarios when we need that. One is the smart grid. We know the grid, they have electricity, from the power plant. If you look at the Singapore, it's more than 90% the electricity produced by burning the natural gas. We know that's not the ideal, right? And even that, the energy demand in the daytime, nighttime, so they're not stable. And to maximize the efficiency, for the power plant and stabilize the grid, obviously we need to have some energy storage system can buffer the use. And especially so if there's a penetration or there's a certain the weightage, from renewable energy, like the famous dark curve I shown at bottom. Of course, so here it's not the data is not from Singapore, it's from California, I think some years ago. So they monitor the energy production and energy consumption, from the morning to the night. Look at in a period of time. So we know that's from like 9 a.m. all the way to 6 p.m. So that's the period you have sufficient the sunlight. That means there's a lot of electricity that generate from this renewable energy, the sources. So then, so the electricity produced, for power plant, it can be reduced. And this is not stable. You look at in the early morning, before the 9 a.m. or after 6 p.m. So the energy demand increased, but unfortunately, so this solar energy, solar electricity disappeared. So that gives, this uneven the distribution of energy demand requirements. Then we need the energy storage to buffer and to stabilize and to maximize the performance of the grid. So what the kind of energy storage can use for such the use? Obviously, there's many technology has been implemented. For example, the most widely used is pump hydro. They just built the dam. And when there's a surplus of electricity, it just pump the water to the certain height. When there's need, let the water flow down to drive the turbine to generate electricity. And actually that's the most mature, the technology allowed the storage of electricity in the really the large scale and the relatively low cost. And another emerging the technology, so that's the so-called compressed air energy storage. So they have like the K underground, so they can store high pressure the air. So they can pump the air when there's surplus electricity. When there's need, so they can let the air release, so they can drive turbine for electricity production. And also for the flywheel. Flywheels is just store the energy in the form of kinetic energy. But the technology is meant for the high power application. It's not for the long duration. If you look at the hydro pump hydro or even the compressed air, it's highly dependent on the site or the location. So where you can apply this technology. For example, in Singapore, they have a so small island. We don't have such the place to build a dam, to store the large amount of the water for the electricity generation. So it's highly dependent on, the location is not applicable everywhere. So then it comes, so why the electrochemical system is so important? So that's another question I want to answer. The gradually go into why we need the electrochemical energy storage. Okay, before I talk about electrochemical energy storage, I like to spend maybe a few seconds on energy quality and the quantity. As I said just now, there's different energy form, from the thermal energy, to the chemical energy, mechanical energy, or electricity, the photo energy, the form. And to this graph to show, for the different energy, the form, they may have a large quantity, like the waste heat. The waste heat can be found everywhere, right? But if you look at the quality, so it's not that easy if you want to use the waste heat, especially when the temperature of the waste heat is low. If a little bulb of environment, the temperature, based on the Carnot cycle, we know the thermodynamic is shown. The efficiency is very, very limited. And if you look at the different energy form, you want to easily use this energy. Obviously, so electricity, has the highest the quality. So that's why it comes to the point. So if we want to use the energy, electricity, that's the most convenient form, and that's the most useful form, and actually that's the case. But if you want to store the energy, if you look at the different energy form without considering the nuclear energy, we know the nuclear energy is something the beyond the scope is different. It's a lot of argument. The places they have different the view. Some they want to open up more nuclear plant. Some want to shut down the nuclear plant. But here, if without considering the nuclear energy, so the storage of energy in a form of chemical energy, so that it has the highest the density. You want to store electricity. We know the electricity itself, you can store that like in the electrostatic way, but the density is not that high. We need to store the electricity in a different form. And this form, if you compare the energy, so the chemical energy, like the one we use from the fossil fuel or the different fuel, even the one from renewable energy, if we store the energy in a chemical bond in a form of chemical energy, it has highest density. So you can think about like the battery use your mobile phone or the laptop, so they can run for the whole day, right? For the piece of battery, that's because for the size of battery, they can store the relatively large quantity of electricity. But if you store in a form of the thermal energy or in a form of electrostatic, the energy like supercapacitor, I don't think it will run for the whole day. So that comes to the point why we need energy, the conversion of storage between the electricity and the chemical energy. And another advantage before I move to the next slide is the energy conversion storage between the chemical energy electricity. So they can be achieved at different conditions. Especially, they can be done at ambient condition. So this ambient condition, for many the applications, so they're very important. Unlike the thermal energy storage, if you stored energy in a temperature like a few hundred degrees, I don't think for the portable electronics they're useful. And this can be scaled, to the different level that make application very flexible and adaptable. Okay. So how we can achieve this electricity and chemical energy conversion and storage? Obviously, so we need to use a device. We call this the battery. And this battery, if you look at today, so that's different the type, that's different the models. So they use different material and apply in the different places. Like the one I shown here, then we have the dry cell. It's just a primary battery you can easily buy from the grocery. And we have the lead acid battery. I believe most of the car will still carry the lead acid battery, even for the gasoline car, for the starting, lightning, for ignition. And for the special use, medical use, like hearing the device, you will need a zinc air. It's also primary battery or even a button cell. And of course, this portable electronics, the phone or the laptop, and to use in a car. And today, the new technology can be used for the large scale, that's a flow battery. So that's the very different the configuration compared with the conventional batteries. So for the development of the battery, that's along the history. We know if you talk about electrochemistry, of course, some people think the it's even the early end, what the Galvani observed, like the lag experiment. But if in terms of the battery, start from the voltaic pile. So then gradually you look at the battery technology. I shown the milestone. I shown so here, from the volatile, to the Daniel cell. The Daniel cell, the divide into the Leclanche type, the dry cell. We still use today, as I said. So the zinc, the manganese dioxide, so they can use the Leclanche type or use alkaline. And the very important, so this lead acid battery, from the plant. You look at, it was invented in 1859. So today it's more than 160 years old, but still widely used. So it is a very long, this technology is very special compared with other technologies. Some appear in a period of time, so then disappear. But the lead acid battery is still used today. And later I'll come back to this point. So that's further development, for the lead acid. They have a so-called super lead acid, okay? And they have a nickel, cadmium, or they have nickel, the metal hydride. And today, we know the important state-of-the-art, the battery technology. So that's the lithium-ion, the batteries, from the portable electronics, to the electric vehicle, and now even in the large scale, the stationary energy storage, that's quite large application. And since the lecture, to the student, I try to show the fundamentals, for this. How to achieve? We have the battery technology using the different materials and the different reactions. What is, the fundamentals, the principles, for the batteries. So here I have two slides very briefly. So one is for the thermodynamics, so the other for the kinetics. It just very let you know, what governs the operation of the devices, from Leclanche, the dry cell, into the lead acid, the nickel cadmium, or nickel metal hydride today, the lithium-ion battery. Okay, so for the battery, thermodynamics we call is electrochemical system. In a thermodynamic, you have a different system. They have otherwise simple system, just look at thermal, mechanical, and chemical. But for the battery, it's a bit special. In addition to the thermal, mechanical, and the chemical, so we have electric field. So we have to look at the role, by the electric field is formed at the electrolyte interface. So if you look at equilibrium, for this electrochemical system, so we need to look at, all the different effects. As I said, the first is thermal, the second is the mechanical. So then the third, that's electrochemical, not just chemical. And in a chemical, we use chemical potential, right? But here we have a Milky bar. The bar that means the electrical part. So they have electric field. So then we have electrochemical potential. And at equilibrium, it has the conditions. It should have a thermal equilibrium, the temperature the same everywhere. And the mechanical equilibrium, the pressure the same everywhere. And the electrochemical equilibrium, that means the electrochemical potential, it should be balanced, reactants and the products. And to make electrochemical cell, I think they have some essential components. You look at, the cell as shown here. So one, you need at least 2 electrodes. And one is you need electrolytes. And electrolyte, we know, so these are the ionic conductor. They can be liquid, they can be solid, but it must be an ionic conductor and an insulator for the electron holes. And this electrolyte solution, so they separate the 2 electrodes. And the 2 electrodes, at least it should be electron hole conductor, or it can be semiconductor, so that's okay. And with the 2 electrodes, it can form a circuit. And based on the Gibbs free energy, the change, if you connect the 2 electrodes together, so this electrochemical cell, they can operate in a different mode. If the Gibbs free energy, the change before and after reaction is negative, we know in a thermodynamic, it shows is a spontaneous. Spontaneous, it shows the galvanic cell. It's just like we discharge a battery. We know the battery discharge process is natural, right? It's spontaneous. And if the gift energy change is positive, we know that's not spontaneous. Like the charging process, we need to provide electricity. So then this cell, we call it electrolytic cell. So the galvanic cell, electrolytic cell, if you use a battery as example, it's just the charging or the discharging and the charging the process. It has the gift energy change, okay? And if at equilibrium I mean at open circuit, there's no current flow. So then your set voltage is determined by the few factors, the standard set voltage, the temperature, and also the very important, so it's a Prof coefficient of the cell reaction related to the activity of your reactant products. So I'm not going to show the details. So these are the thermodynamics. So at a different operation mode, for the typical electrochemical cell. And equally important, or maybe even more important, so that's kinetics. So the kinetics, so these are the critical, for the actual operation for the electrochemical system. We know thermodynamics normally, especially for the equilibrium, thermodynamics, we're talking about the system at equilibrium, that means there's no current. That's not, the condition to want to use a battery, right? When you use a battery, there always, no matter it's a discharge or the charge, there's always current flowing through the system. And as this, the kinetics will become very important, for the battery performance. So the key in a electrochemical system is the electrolyte interface. No matter you're talking about lead acid battery or a lithium-ion battery, so the key area or the part, if compared with other system, is always the electrolyte interface. You look at the photo here, so it have zoomed in, the graph is shown. So one side electrode next to the electrolyte solution, so they have the so-called double layer, the form. And this double layer, so they have electric field. So that's the place you have electrochemical reaction. And once they have the current flowing through the system, and your system will deviate from equilibrium, then you have the over potential. So the potential will be different from the one you measured at open circuit state, that's equilibrium. So they may have this over potential for one electrode, for the other electrode, and also for the ohmic, the series resistance. And the very important topic in the electrochemistry is to study the dependence between the over potential and the current, for the different kinetic process. You may have this activation polarization together with the concentration polarization. So you may have the over potential observed at the interface. And also you may have this ohmic, the polarization. So altogether, it will determine your voltage during the discharge process and during the charging process. And not only that, if you look at the different battery technologies, from the dry cell to the lead acid battery, to the nickel cadmium battery, all the way to the lithium battery, look at the material we use in a battery. Nearly all of this, the battery, they operate at some dynamically unstable condition. If you look at the dry cell we use the zinc manganese dioxide. And you look at the zinc, the potential thermodynamically, obviously it's not stable. We're never in contact with water because the zinc is always tends to reduce water form of hydrogen. And another example is the lithium-ion battery. Lithium-ion battery, you look at the negative electrode material, so the potential is so negative. All the different solvents in the electrolyte, it got reduced. So thermodynamically it's not stable. But unfortunately, so we have the kinetics that comes in. So the kinetics, it can make the device, it can work, although the thermodynamically they're not stable. Like the zinc. So we can suppress the hydrogen formation, we can stabilize the zinc. So you can slow down this reaction, for the lifetime of the dry cell so we can still make it work. And for the lithium battery, if you are familiar, with the battery chemistry, we know it's very important is SEI. So this SEI layer will form on the surface of the electrode, and SEI, so they are insulating to the electron, but conduct the lithium ion, so they can protect the material underneath. So the kinetics, it played a very, very important role, not only for the actual operation, and also for the use of the material which is not thermodynamically stable. Okay. Okay, now let's look at for the battery configuration. If I summarize, there's two types. So one is one I shown on the left hand side. So that's a so-called you can call it enclosed the structure, and with the material, the solid electron material coated on the electrode sheet. And they have a negative, positive electrode sheet, and together, with the separator to form a sandwich type. They can form a jelly roll, so they can make the battery, by inserting this jelly roll in the battery case. Or you may have the so-called the bobbin type. But no matter what the battery configuration for this type, so you have all the positive and the negative and the electrolytes of the material, they're all together in the same place. So that's one type. And if you look at the one on the right-hand side, so they have a very different battery configuration. So the energy, the storage in a two electrolyte, the tank. One is for the positive, the other for the negative. And the power that generates in the middle, they have the cell stack. In other words, for this kind of battery, the energy storage and the power generation, they're not in the same place. For the solid electric battery, as said, all the battery material, together. But for the one on the right-hand side, actually we call it redox flow battery. So they have a decoupled energy storage and a power generation. And the electrolyte in the store, they just store the electrolyte in the two tanks. When a battery in operation, you have the two pumps. So the two pumps, they can circulate the electrolytes, from the tank into the cell. And the species, they can react on the surface, produce electricity, or they can store the charge. So these are the different battery configurations. Of course, the battery we use today is this kind, like the one you use in your mobile phone. But for the large scale application, the redox flow battery with the decoupled energy storage and the power generation, it has the special, the flexibilities. For example, it has better safety because the energy storage, the media is not together, with your the cell stack, and also so you can scale the capacity, by simply increasing the size of the tank, right? And if you want to increase the power, then just have a more cell stack. So that means the capacity and the power that can be changed independently. This is not the case, for the solid electric battery. For the solid electric battery, you want to get a more energy, you have to get another battery, right? But for the flow battery, so we can change that independently. And also they can have a modular design. It can make the scalability a lot better. So that's why the later I will spend quite some slide on this battery technology, the redox flow battery. Okay. Okay, so now let's go to the important part of today's talk. So the large scale chemical energy storage technologies that people developed in the past and be used today, and emerging technology in the future. Okay. What kind of the battery technology can use in the large scale? As I said, in the large scale, it's not for electric vehicle. So you have the 100, like a kilowatt of this kind, or kilowatt hour. So we're talking about the megawatt or even larger the scale energy storage. If you ask me, so what battery technology can be used for such application? Of course, the different technology I shown previously. So like the lead acid battery or the nickel-based, like a nickel cadmium or nickel metal hydride, the lithium battery, including the radar flow battery or the molten salt battery. I'm going to show that later again as well. All these battery in theory, so they can be used in the large scale, not only for the small size, the part of electronics, but for the large scale application compared with the consumer electronics or even for the electric vehicle. So that's different matrix for the use. For the part of electronics, as I said, so we hope the battery, so as small as possible and as light as possible, and it can store as much the energy as possible, right? So that means, so the energy density, no matter is volumetric or the gravimetric energy density for this kind of battery for the part of electronics, they become very important. But the large scale, the use, that's different. So here we're talking about the stationary energy storage, no matter for the grid or for the distributed energy storage for the solar farm. So the battery will not be carried or not is mobile, it's just stored somewhere. So the size is not that critical. In other words, so the energy, the density is not that critical. But if you look at the scale, we're talking about the megawatt hour or the gigawatt hour. So that means it will store a lot of electricity and it will consume a lot of the material. And with this in mind, so then I believe you agree. So the safety will become the very, very critical for this kind of application. You can imagine even for the part of electronics, the battery catch fire is still cause trouble, right? And it have electric vehicle, if they burn, can be a big accident. But if there's a megawatt hour, the gigawatt hour, the battery, the pack in the place, they catch fire, they become a big disaster. So the safety, so that would be the most important, for the large scale energy storage. And secondly, the cost. As I said, we're not talking about the material they use in a gram, a kilogram, the tons. So here, so the material consumption will be 1,000 tons, a lot more. If the material the cost is high, I don't think this technology is affordable to people. And actually that's the case. And if you look at the technologies, so which has the potential to be used for the large scale, so the cost, including the capital cost or the levelized the cost, they become the important measure. And look at the battery technologies based on the stage they have. Some already been mature, some in a deployment stage, some in a demonstration stage, some are still in a development stage. No matter what the technology is, and we know there's a target for the DOE in the large scale application, like the cost would be lower than $100 per kilowatt hour, right? So you look at this, so then many of the technologies so we have today, there's still a gap if we use in the large scale. So that means, for this kind of application, you look at the technologies we have here. We need to look at the measures from the one we use in the part of electronics or the electric vehicle. So the safety and the cost, it becomes they become more important for the large scale use. And based on the ranking of the measures from the safety, the cost, the performance, so I would say, so the battery technology, the radar flow battery, the molten salt battery, they compared with lithium battery, so there'll be as an advantage. Although, like a lithium battery, have been so mature and the energy density is so high, but if you look at the safety and potentially the cost if you have really the large scale use. And we know the lithium batteries may have, there's no sufficient lithium or the cobalt nickel, for such large scale use. We need to have alternative, the material and alternative battery chemistry, for this kind of application. Okay. So then I go to, and with this in mind, I will highlight mainly the two types of battery technologies. So one is the flow battery and the other molten salt. Because these two technologies have been developed for quite some time, and with the hope, so they can be used in the large scale because they were developed actually just suitable for the large scale use. It's not for the portable electronic for the mobile use. And the two technologies has been demonstrated in a quite large scale, although it's not in a commercial, but some project may call this commercial, but it's not so widely deployed. So let's look at how these two technology works, and what is the principle, and what's the status. Okay, so the first, the redox flow batteries. The redox flow batteries, as I shown in one of the previous slide, when I compare the battery configurations. So the flow battery, they have very special, the structure. And it's different from all the rest. It's only the flow battery have such the decoupled energy storage and a power generation. If you look at here, obviously, the energy storage media in a flow battery is kind of the chemical components that dissolve in the liquid. Because energy storage media need to be circulated from the tank to the cell. That means it must be flowable. If it's a solid, so will not be the redox flow, right? And also, since you have the different electrolyte solutions, and these two electrolyte solutions cannot be mixed. It's just like in a conventional battery, the two electrodes cannot be connected together, otherwise it gets short, right? So then we need a special, the material, so that's the membrane. So this membrane, you can separate the two electrolyte solutions, but it still allow the transport of the charge carrier, so they can close the circuit. And these two electrolyte, the solutions contains the redox species. And one in a cathode, you have reaction. And one in the anolyte, you have a different reaction. And based on the potential difference of these two reactions, the half cell reactions, so you can have overall the cell, they have a voltage output. So when a flow battery in operation, so the two pump, the circulates, the cathode, anolyte, between the tank and the cell, and the species, the react on the surface or the interface, electric interface, so it can produce the power or it can store the energy in a tank. And obviously, so here, if you look at the energy, it can be stored in a flow battery. The one is the cell voltage. So that's the potential difference between two electrolyte solutions. And also the capacity. So the capacity, so that relates to the volume. Of course, you have a large, the electrolyte tank, it can store the more charge. And also depend on the concentration of this electrolyte solution. Because in the end, it's the volume, the times concentration to give you the quantity of the redox species, right? So you want to store the more energy in a flow battery. So then we need to have larger cell voltage, and also you have larger concentration, or you have a larger cell, the volume. But if you look at volumetric capacity, of course, you need to look at the concentration, okay? And the redox species can be used in a flow battery as long as they are soluble in a solution, and they have the reversible, the redox reaction on the electrode. And the battery chemistry has been developed. And for the flow battery, the technology, I think the most widely accepted, the people, the NASA in the 1970s, so developed the first, like it's based on the iron, titanium, or the iron, the chromium, the flow battery, but the French people disagree. So they think nearly once the century, I think earlier, so the French people, they already, in the military, they already developed the flow battery, but in the chemistry, based on the zinc and the chlorine, or the zinc and the bromine. But none of this system, so they can operate in the long duration, is mainly because the cross-contamination, for example, like this iron, the chromium. So one side iron 2+ and a 3+, and one side the chromium 2+ and a 3+. And this, the two pair of the redox species that dissolve in a cassonite and analyte. And across the membrane, so this ionic species, they can get mixed. And once they got mixed, we know that's kind of the self-discharge, right? And once they got mixed, it becomes very difficult to separate. So it become a critical issue, for this kind of the flow battery. And I think in the 1980s, there's a new battery chemistry developed, the so-called all-vanadium flow battery. So the inventor is Maria Scalas, from University of that's in Australia, New South Wales, and she already retired. And she proposed the battery, they use the vanadium species on both sides. In an analyte, so we have vanadium 2+ and a 3+. And in a cassonite, we use vanadium 4 and a 5+. Vanadium, they have different valence states, right? And in the negative side, so the reaction between vanadium 2 and 3, they give you the potential minus 0.25. And a reaction of vanadium 4 and 5 in the positive side give you this potential, nearly 1 volt. So then overall, so you have the cell voltage is about 1 volt. And look at, on both sides, no matter what valence states this vanadium species are, they're still the vanadium, right? Even they get mixed, they have a crossover, but it still can be converted back to the valence state. I mean, chemically, so it can be easily restored. So that makes this all vanadium flow battery is more interesting, for the practical applications. And for the vanadium flow battery, you look at vanadium, the species in a different valence states. As the 5, the 4, the 3, and the 2, they show different color. And if we make them into the cell stack, of course, they have, so that's only the cell stack, not electrolyte tank. So they have 2 electrodes. They have the current collector, and they have electrodes. They can allow the electrolyte to flow. And these 2 compartments are separated by the membrane. And the electrode we use, the current collector is a graphite plate. The electrode, the carbon felt, and the porous structure, if it flows through the design, so the solution can just flow through the pores. And the membrane, because here the charge balancing species is a proton, then we need the cation exchange membrane. We know it's the nephew, the membrane can separate the charge. And if we make into the battery system, you look at the one on the right-hand side. So you have the battery stack here, and you have 2 electrolyte tank at the bottom. And one is negative and the other positive. And we have the pump, so the electrolyte can circulate into the cell. It can make power. So that's a vanadium flow battery based on the special battery chemistry. So it become more promising. And actually, that's the mature, the flow battery technology we have today. And for the deployment of vanadium flow battery, as I said, so since it was invented in the 1980s, has been more than the 40 years, right? And even the earliest and the lithium battery, but unfortunately, so the application of vanadium flow battery, I mean, is not that the great. Of course, the recently there's more and more installation of the flow battery, the project, the worldwide. So the few companies, so they are producing the vanadium flow battery in the world. I think the biggest one is the Runke Power. So that's the one from China. And another company, so that's the Sumitomo Electric, the Japan company. And it's, if you look at the Runke Power that recently, so they have, I mean, a huge installation of the vanadium flow battery in Dalian city. So they have the project, so that's around 200 megawatts for 4 hours. That means 800 megawatt hour, the storage. That's really a large project for the vanadium flow battery. And if you look at other places, there's a map that shows the different project in the world. The main issue for the vanadium flow battery is the cost. As said, there's a few, the matrix, for the measure of the technology. So the safety, the vanadium flow battery, at least compared with the lithium battery, that's an advantage. But the issue is a cost. So the cost, that's different the parts. It contributes to the total cost. And look at the majority, so here, it comes from the electrolyte. That means vanadium. I mean, vanadium, the cost in the past few years is up and down. It is mainly because, like the 2 years ago, so so the vanadium cost that went up by the few times because vanadium, they have the more application is stainless steel. So there's more vanadium consumed in other places. So to make it viable for the large scale use, so we have to reduce the cost. And to reduce the cost, I think obviously one way is to use alternative the material, which have a low cost instead of the vanadium itself, right? And I said, so based on the flow battery, the operation, the principle, there's different, the soluble redox species can be used in the battery, right? As long as soluble in a larger concentration, and it can produce the good voltage, that it can be used for the flow battery application. And actually that's the case. There's many, the battery, the chemistry has been developed for the flow battery the use. And some the inorganic and some the organic. And recently, there are more organic redox species been developed. Some like the quinone, some like valogen, some like phenazine, and some they have a tempo or the ferricene. So there's different species. They have the different potential, the regions. So it can be used at a different electrolyte condition. Some is for neutral, some is alkaline, some is acidic. There's many the publications, in the field. But for the organic, the species we know in series, so they are abundant enough because mostly they are considered carbon, oxygen, hydrogen, right? But I had to look at long-term stability. And for this inorganic, the material, so that the advantage, they're relatively stable. But if you look at, for the inorganic, you just look at in the periodical table, it's just the few, the elements we can choose from, right? So maybe the combination of these two can give us the more opportunity, for the viable the battery chemistry in the flow battery use. Okay. Okay, before I finish the flow battery the part, I have one slide, for the new development of redox flow batteries. And for the new development flow battery, is mainly, with the purpose of increasing the energy density. We know the energy density for the flow battery might not be that critical, but for some special use, people still want the battery become more compact, so that the footprint can be smaller, especially Singapore. So the land is so expensive, so you want to have this battery system just occupy the space. And to enhance the energy density of the flow battery, there's two approaches the people been exploring. So one is the so-called semi-solid flow cells. As I said, the capacity for the flow battery, for the volume, it will depend on the concentration of your redox species. And the concentration of redox species in the electrolyte solution is limited by the solubility. Like the vanadium, so normally we use like 1.25 the mole. You want to enhance that, you have to increase the concentration of the acid that make electrolytes more corrosive. So there's always a limit. And if you look at the energy density, in a conventional battery, like a lithium battery, so the capacity is order of magnitude higher. I mean the volumetric capacity. The reason is the energy stored in the solid material. The solid material, of course, is much denser than the liquid solution. So then the people, they came up with the idea, instead of using the soluble species, so they have the suspension of the solid particle. Suspension of solid particle, they form a slurry like this kind. So this slurry is a mixture of active material and with the electrolyte solution. It itself is still flowable, right? It can be stored in the tanks. It can be pumped into the cell, producing electricity. So then it can make the effective concentration of the charge a lot higher. So that's the semi-solid flow cell proposed by, I think in the very beginning, proposed by the research from MIT, Professor Yamin Chan's group. So they want to use this kind of the battery, the configuration to enhance the capacity. And they use the lithium battery material and make it into slurry, then flow through the cell. But later they found, to make it work effectively, you need to add a lot of the conducting additives, because so the particle, if they're not connected, the charge, they need to percolate through one particle to another. There's a lot of resistance. You need to add off the carbon, a lot of carbon additives, so they can form a continuous percolation, the network can make it work. And with these carbon additives, of course, can reduce the capacity and also to make the viscosity high. And then, for the flow, they become more difficult. But there's still the interesting approach. The people apply this idea, with different battery materials, including the one use water-based electrolytes, become safer for the large-scale use. And the other the approach is the so-called redox-mediated flow battery. But here we use the lithium battery material example, can call this a redox flow lithium battery. It's different from the semi-solid. Instead of forming slurry or this viscous, the flowable, the mixture, so here the material they just store in 2 tanks. They're not flowing with electrolytes. So the materials can make into the granule, the bigger particle. They can they're kept in the 2 tanks. Only the electrolyte, they're flowing through the tank and the cells. So then you can imagine, so this can make the storage of the solid material a lot higher, right? Because no need to care about the viscosity, because only the liquid are flowing. And but here, since the solid material, they're not reacted on the surface of the electrode, then we need a special mediator. So this mediator is like the redox species we use in a conventional flow battery. So they can bridge the material in the tank and the electrode in the cell. So they can react the material and carry the charge back to the cell, for discharge or for the charge. So in a sense, so this approach is the one we develop here. And later I will spend some time to give some example, how this battery technology work. Okay, I think I stop here, for a while. We have a 5 minutes break. So then we come back. I will skip the part on the molten salt battery because we don't have sufficient time. We just jump into the technology. So we develop here and give you the highlights for the latest development. Okay. And we'll come back maybe in 11:15. Okay. And if there's any short question, we can also discuss during the break.
Can I ask you a question?
Sure. Yeah.
Yeah. Oh, thank you for the great lecture. I'm not really familiar with the flow battery. I can really learn a lot from your lecture. So
thanks.
Yeah. So you showed the old vanadium flow battery, and then you introduced the alternative material that can replace vanadium. So I can understand the usage of the transition metals because they have multiple valences. But what about the organic materials? So what are the advantages of using organic material for a flow battery?
Okay, as I said, for the inorganic material, I mean, there's only limited the selection. If you look at the periodical table, right, it's only the few elements that can be used for such the purpose. We will need to look at the solubility, and we need to look at the potential, and we need to look at the reversibility or the stability, and also the cost, right? And for the organic redox species like the quinone or the ferrocene, or like the viologen, these are organic, the material just consists of like a carbon, oxygen, or hydrogen. In theory, they are more abundant, right? It can make cheap. And we can adjust the potential, by adding the different substituents, the same to the solubility. So it can make polar, and of course, we are talking about the aqueous solution, use water as solvent. That means a lot of things we can change, we can adjust. But of course, for the organic system, the main concern is stability. Because the structure, they have different groups. And we're talking about like 10 years or the 15 years to use. You can imagine if, organic, they may have degradation gradually. But I mean, we make a compromise, right? So if it's really cheap and really, I mean, in terms of the solubility and other the properties, we can still use that. Even the stability is not on a par, with inorganic. I mean, it's still in the developing stage, so no one knows which one will win out in the end. But overall, it's not, decided by our researchers, right? It's by the industry. So what
Right.
the system we're going to choose. Yeah.
See. Yeah. Thank you.
Yeah. Okay. I think we just carry on. Otherwise, I cannot finish the slides here. You don't want to make it too long. Okay. Okay. Just now, I don't want to say the brief introduction. I still the brief because we normally spend 2 lecture time, for this part. But I read a lot of things we can cover. But let's go to the second part. So what we are doing here, I mean, in a context of a large-scale energy storage in Singapore. As I said, for Singapore, it has owned the target, for the decarbonization, or I mean, for the mitigation of the climate change. The strictly follow, the target. So I mean, in the research area and in the industry, the sector, so that's different. I mean, the practice have been implemented, to cut down the carbon emission. And one important area is the energy storage. Energy storage, as I shown one of slide previously, one important area is the smart grid. For Singapore, the most of the energy imported. Although I said the solar energy and the wind, I mean, there's no limit, right? But the solar energy is proportional to the area of the land or even the sea land, right? But Singapore small. In the end, the majority, the energy, we are not talking about the nuclear, so still to be imported in from other places. And we mainly talk about the smart grid, and maybe small, on the PV farm. And unfortunately, we don't have much wind here. So, the main target, the energy storage, the technology allow the smart grid application, and this technology, they have a relatively small footprint. That means there's one important measure, that's energy density. You want to make the system more compact and small. If you talk about the vanadium, the flow battery, the conventional flow system, they are the bulky. So we have the motivation to reduce the size, and that's one of the things I'm going to introduce, how we can enhance the capacity for the flow battery. And to make that happen, it's very important. The process we're based on is the redox mediated process. In the beginning, I have a few slides on the fundamentals of electrochemistry, right? And very briefly, we talk about the thermodynamics, kinetics for the electrochemical system. And I said, so for any electrochemical device, it's always electrolyte interface centric. So this EE interface, electro interface, is always the critical, dominating the operation of the different battery devices. So we need to optimize this interface, can facilitate the reaction or facilitate the different kinetic process. But if you look at the large scale application, so this electro interface, it will have this inevitable limitations. So one limitation is to look at electro compartment. It has the limited space. Look at the foam battery. So you have the active material, the coated on the electrode sheet. You have 2 electrodes, the centrifuge with the separator. So the outer layer, they're tightly pressed together. So they want to squeeze more material so that it can store the more electricity. So they have a limited space if you look at this electrode compartment. And the second is, such conventional use may impose the limitation of the electrode material catalyst, because this electrode material or the catalyst, so their on the surface of electrode. As I said, for the electrochemical cell, the two electrode, it should be electron hole conductor. But unfortunately, some electron material, the catalyst, so they are not the good conductor. One example is the lithium phosphate. Itself actually is very insulating. To make conducting, we need a cold carbon, right? Or we need to have doping or other method to enhance the conductivity. And this already ruled out a lot of the material potentially that can be used, for this kind of application. And also, you may have sophisticated electrode interface, especially it involves more than two phases. We know the electrode interface normally is a solid liquid interface. They involve two phases. But if you look at some reaction, they may have the formation of the new solid phase, or may involve the gaseous phase. For example, the air battery. They may have oxygen, or they may have even hydrogen, and with the product, it may be insoluble. So they have very sophisticated electrode interface. Then how to, if we can mitigate, so this limitations on the conventional, the E interface. So then we can open up the new opportunities, and especially, for the large scale, the use. And this, so we can achieve based on the redox mediated process. And what is redox mediated process is the one I shown on the right-hand side, the graph. So the one in the box is the conventional case. So you have two electrodes and separated by the electrolyte solution. And we have all the limitations as I mentioned here. And to separate, the critical reaction from the surface electrode, to the different places, so that we need additional process we call the redox mediated process, with the help of the redox, the mediators, so they can shuttle between the electrode and the reactor tanks. Something like the flow battery I mentioned, they have two tanks, right? But now, so we have in a tank, not just liquid. So you may have energy storage material, or you may have a catalyst, for the different reactions. So this, it can lead to the electrified, the chemical engineering process, so that allow a large scale application, not only for the energy storage, also for the conversion, is even for the variable the chemical synthesis of the processing. Later as said is one example, hydrogen production. Okay, and especially the useful for the open system of operation. So we are talking about the large scale, and if the system is open, can make it more scalable, is more flexible, right? Especially we have the feedstock, from like the air, like the water, oxygen, nitrogen, the CO2. So the open system, based on this redox mediated process, that become the more relevant. Okay, and so here I will mainly give you two examples. One is for energy storage, and the other is for the conversion, so hydrogen production. And for the energy storage, as I said, the conventional flow battery, like a vanadium flow battery, we store the energy in a vanadium solution. You look at the energy density compared with the lithium battery, it's 1 order magnitude lower. It's mainly because your concentration of your vanadium species is low if you compare. So the concentration is just 2 mole. And you look at the lithium battery material, so the effective concentration of the charge is typically about 20 mole. That means 1 order magnitude higher without considering voltage difference. So to enhance the capacity in a flow battery, the one natural way, if you look at here, is to fill the liquid electrolyte tank, with the solid, like the one I shown here. If we use the solid material in a tank instead of liquid, so then in theory, so the capacity of the tank will be comparable to the one you use in a conventional solid electric battery, so like a lithium battery. Of course, depending on material you use. And how to achieve that? If we have the solid material, like the one I shown here, they have the granules, the big particles, is just put into the reactor tanks, and the electrolyte is just the flow through and react with the solid material, like the one here is porous. So it can carry the charge from the tank to the cell or the other way around. So then we need a special process. We call this redox targeting process. And this redox targeting process is just one redox mediated process. It's between the molecule in the electrolyte and the material in a tank. So the molecule when it flow into the tank, it can react with the material. It can oxidize material or it can reduce material for the different process. So then the charge can be extracted or it can be stored. So here I give one example. We based on the redox species. So that's the ferrocene derivative. It has the imidazolium, the positive charge. The species can enhance the solubility because it's charged. And here we use the lithium battery material. We know that's the very widely used material in the lithium battery. But instead of coating the material on the electrode, so we make the material into the granule and put it into the tank and let the electrolyte containing this ferrocene derivative to flow through the system. And if you look at the potential of this molecule, it's exactly the same to the material. So that means based on the Nernst equation, when the more and more the molecule got oxidized, so that it generates the potential difference. So this potential difference will drive the oxidation of this material. It means the material will be oxidized to become iron phosphate, and the lithium will go to the other side. So that's the charging process. And this charging process just the reverse. And with that, if you look at the voltage profile on the right-hand side, if without having the solid material, so the capacity is limited by the molecule only. But if you have this solid material in the tank, so then the capacity can be greatly extended, with the contribution of the solid material. So let's give you an example. We just store the material in a tank. So it still can contribute to the capacity. And the operation is just like a flow battery, right? So we only have the flowable electrolytes, like a conventional, the battery system. Of course, here it's just a half cell because the other side is just the lithium, the metal we have on the electric sheet. It just to demonstrate the concept with a single molecule. We call it single molecule redox targeting reaction. So we can simplify the composition of the electrolyte. And another example, as I said, we are targeting at large scale use, right? So we want to use a more abundant material. So we get rid of lithium. We use the sodium. Of course, the vanadium still relatively rare, right? But it's just the demonstration. We use the sodium vanadium phosphate. We know that's a widely studied material in a sodium-ion battery. And we store the same material in these two tanks. And we write the molecules. One is fluoreno and the other is phenolsalzane. So they can react with react with the material in the two tanks. So they can generate the charge. In other words, we only have the solid material stored in the tank. Then the system operates like a flow battery with the two electrolytes, one anolyte, the other catholyte. So the capacity is determined by the solid material. And the power is produced by these two molecules in the electrolyte. And obviously, so the capacity will be greatly enhanced because this material have much denser the charge density, but it still have the decoupled energy storage and power generation. There's another the demonstration based on the different battery chemistry. But for the practical use, I don't think the organic electrolyte, is a good idea, for really large scale application because organic, the solvent normally are flammable. So we want to use the safer electrolyte, the system, for example, use a water as solvent. So here, so we have aqueous, the system, and based on another, the cheap material, the Prussian blue. The Prussian blue, we know that's the pigment. this iron ferricyanide. It's very cheap material. It's been widely used in different places. I know recently the Prussian blue or Prussian blue analog material has been used in a conventional battery, including sodium battery. But here we just make the Prussian blue, the granules like these honeycomb structures. They have a pores. The electrolyte can flow through. So we store this Prussian blue material in a tank, and I use a very stable the redox species ferricyanide. If you study the electrochemistry, we know the ferricyanide is a very important redox species we use all the time in a water-based electrolyte. It's very stable, and itself, it has a decent solubility. So the ferricyanide, it can react with the Prussian blue for the charge and discharge. So then it can make the flow battery much safer. And so the photo, the one shown here, so there's a 500 watt the system, and one side, and we have this Prussian blue, the honeycomb, the solid, just put it in a tank, and they have ferricyanide electrolyte, the flow through the material, so then it enhance the capacity. Okay, and this system is extremely stable. There's no capacity drop in a few hundred cycles. I think here that's nearly 2 months the continuous operation. Okay, and the redox mediated process, it can be applied to the different battery system. And just now I mentioned it's more on the conventional flow battery. We just have the storage material in the tank and still have the conventional electrolytes. And we have enhanced the capacity. And the same idea, it can be applied, to the more advanced battery system like the lithium-air battery. When the lithium-air battery, in theory, it has the highest energy density among all the different battery chemistries. The reason is the lithium itself is light, and it has the potential is very negative. And the oxygen, if you think the oxygen, they can be obtained from the surrounding air. So then we can only have the lithium as active material in a battery. But unfortunately, so this battery, the system, encounters a lot of challenges. If you compare it with the air battery, including the fuel cells, the one reason is, if you compare it with the zinc air battery, for example. So the product, the reaction, the product, the lithium peroxide, if you use aprotic organic solvent, the lithium peroxide is insulating and also is insoluble. That means once they form, it will cover the surface of the electrode, and it will clog the pores and also will passivate the electrode. So that makes the activity of electrode drop quickly. So that's one of the limitations I mentioned previously. For the conventional electrolyte interface, it becomes very complicated. Based on the redox mediated process, we can shape this reaction, from the surface electrode, to the separate reactor tank. So that's the one I shown here. So if you have the redox mediated reaction, that means the reaction of oxygen is not on the surface electrode, but with redox species in the electrolyte. So then the reaction of the oxygen can take place in a separate reactor tank. We call it gas diffusion tank. In a conventional lithium oxygen battery, the oxygen reacts on gas diffusion electrode, right? But here, so we call it a different name, it's gas diffusion tank. So then the formation of lithium peroxide will be only in a tank. And your electrode in a cell is always the fresh. So that means your electrolyte interface is always active. In this case, so we can get around the issues encountered in a conventional lithium oxygen battery. So it can greatly enhance the depth of discharge. In other words, so we can reduce the three-phase reaction in a conventional gas diffusion electrode to the two-phase reaction. One is solid liquid in a chemical reaction on the surface electrode, and one the liquid, the gaseous chemical reaction in a gas diffusion tank. So, and with this, we can greatly enhance the power, for the lithium oxygen battery. Look at here. So we have the lithium electrode in the cell, and the reaction of oxygen is inside the separated tank here. We use the molecule, so it's the quinone and viologene with the spray of the electrolyte, so the reaction can be greatly facilitated. So it can operate at a current, the 15 milliampere per centimeter square. I mean, for the lithium oxygen battery, so this current is really high. And of course, so this kind of the battery configuration only allow the large scale of the use, because you have a pump, and you have the tubing, and you have the separate gas diffusion tank. Basically, it's kind of the battery system. It's not just the cell. So that's another example, I want to highlight. And also, instead of having separate reaction for the oxygen side, so we can have the reaction, for the negative electrode side. So that's an example based on the zinc air fuel cell. We know the zinc air, the battery has been commercialized in a primary the cell, for the hearing aid application. So basically, the zinc got oxidized and become zinc hydroxide in alkaline condition in the presence of the air, right? But you want to make it rechargeable. There's a lot of the barrier you need to overcome. So here we propose, one approach. We call it zinc air the fuel cell. That means we use the zinc as a fuel. Like the fuel cell, we use hydrogen. But the hydrogen, we know, is a gas. In itself, you need to store. We know it itself is not that safe, for the transportation and the storage at high pressure. So the hydrogen itself has some limitations. If you use the zinc as a fuel, there's additional advantage. So it itself is much safer. And if you look at the volumetric, the energy, for the zinc is much higher than the hydrogen. But how to make that happen? So here it is similar to the redox mediated flow cell I had shown previously. We load the zinc granule in a reactor tank. And the other side is just like the fuel cell. So the oxygen that comes in, and your zinc, we load in a tank, and with the help of this redox molecule, it can oxidize the zinc and carry the charge from the tank to the surface of the electrode that can generate electricity. So that makes the operation is very convenient. Whenever you need electricity, just load the zinc, the granules. You can make into the cartridge or in the basket. You can load into the tank, so then the zinc can start to react and produce electricity. And once the zinc depleted, they become a zinc oxide. And the zinc oxide, it can be removed by replacing, with the new cartridge. So that's, the new publication we had recently. If you're interested, you can take a look. Okay, so lastly, I want to maybe briefly introduce a different application in terms based on the redox media process. So that's a combination of the storage and the conversion. The conversion that's for the hydrogen production. So this again is based on the scenario maybe relevant to Singapore for the urban application. We're talking about e-mobility and hydrogen mobility. We know it's a very critical part is the infrastructure. So for the e-mobility, we need to build the charging station for the electric vehicle. And for the hydrogen mobility, the same, you need hydrogen, the fueling, charging station. And there's the main barrier, for the deployment of these technologies. And if we combine these two together, it can provide a way it can reduce the cost. And this is based on the belief, for the charging station, if you believe energy storage is important part, We know for the charging station, when the electric vehicle, they're being charged, it itself will drain a lot of charge from the grid. Especially you want to have the fast charging process, right? For the fast charging, for the one car, you can imagine if 100 the kilowatt hour, you want to charge in 1 hour, they will drain 100 kilowatts electricity from the grid. If you have the few the cars being charged all together, so then the requirement on the grid will be huge. We need to upgrade the power grid. Then important to have the energy storage system. It can buffer the grid, so they can charge the car directly by the energy storage system. So that's the so-called DC-DC, the coupling. And also, you can have the fuel cell car. Might not be relevant for Singapore, but if there's such need, we need to have a charging station for the hydrogen. And the hydrogen can be produced on demand, so that it can make the use a lot easier. Now let's look at how we can achieve that. So that's based on the so-called redox-mediated the water electrolysis process. So this redox-mediated process is different from the conventional water electrolysis. The conventional water electrolysis, is just produce hydrogen, oxygen in the cell compartment, right? And hydrogen in the form on one electrode, oxygen form the other electrode. So there's the limitation again. Of course, there's the commercial, the electrolyzer, based on this. But if you use electricity direct from the PV, there may be some the limitations. And we want to connect the electrolyzer, with a battery. Again, the battery can buffer the electricity from the PV or the wind. And based on the redox media process, we can combine this battery and also achieve the spatially decoupled hydrogen production. In a conventional water electrolysis, so the hydrogen, oxygen, they are produced in the cell compartment. If the pressure of the hydrogen, oxygen high, then we get a cross, we get a contamination, then we have some issues for the purity or the safety. And if you have this kind of the system, in the middle, it's still like the flow battery. But in a tank, instead of having a liquid electrolyte or the solid energy storage material, we have a catalyst. So one catalyst is for the oxygen production, and the other catalyst for the hydrogen production. If you choose the right redox molecule, like a ferrous cyanide here, in the ferrous cyanide, if it got oxidized on the surface of the electrode flow into the tank, then it can produce oxygen. So the catalyst, we use nickel hydroxide. So that's alkaline system. And for the other side, we use the platinum as a catalyst, and the molecule is DHPS, is kind of the phenazine molecules. If it got reduced and flow into the reactor tank, it can produce hydrogen. One side oxygen, the other hydrogen. That means, so the hydrogen and oxygen, the formation, they are shifted from the surface electrode to the two separate reactor tanks. We call it spatially decoupled. So this process, so they can reduce, the gas, the mixing, and also itself, because the flow battery, so your charge is stored in the electrolyte solution, they can buffer the electricity. It's when you want to produce a green hydrogen from the PV or the wind. And that's the operation. So this process can be achieved in a relatively high the current. So with relatively the low over the potential. And we look at the hydrogen production, the process by using the phenazine molecule. Basically, the phenazine will become hydrogenated on the surface electrode and flow into the tank and the regular surface of the platinum. It becomes dehydrogenated. So then the hydrogen gas will form. So that's the process. And based on this approach, so we can achieve the so-called the decouple on demand, the hydrogen production. The on demand, that means when there's there's no need for the hydrogen production. We just store the electricity in the two tanks like a flow battery. And when there's need, when there's demand for the hydrogen, we just let the two electrolytes flow into the reactor tank, for the hydrogen and oxygen formation. In other words, so the hydrogen, they just store in a form of electrolyte. So that can make it a lot safer. There's no need to store the high pressure, the hydrogen, and to share the most of the infrastructure, the facility used for energy storage. And the storage part can be further enhanced by using the solid material I mentioned for the redox targeting process. We have a solid material in the tank, so they can further enhance the capacity. Okay, so finally we come to the end. To make a summary, for the field, the system we have been working on based on the redox media process, so they can be applied to the different energy-related applications. And this application allows us to ship the critical reaction from the surface of electrode to the separated places, for the energy storage and for the energy conversion, including the hydrogen production, and also maybe for the ammonia reduction, for the nitrogen reduction, for the ammonia formation, or even a carbon dioxide reduction. So that can have a scalable, the process, as I said, it's just electrified chemical engineering process, especially suitable for this open system. Okay, so lastly, I'm going to come back to the point. What would be the future energy storage technology, especially, for the large scale, the use? Actually, that's a slide I showed to the students in a module I teach here. So we just look at the periodical table, right? You look at the material we use today, and you look at, the battery, the material, the battery chemistry that been developed. We know there's the battery chemistry material been developed. Based on the old battery technologies, as I said, the lead acid battery that recently have been developed into the super lead acid battery, by using the so-called capacitive effect, you can enhance stability of the lead so it can run for much longer time. So that means the old technology is still evolving. And also for the zinc manganese dioxide, the dry cell, like Langcheer type, it's also more than 100 years that people try to make the rechargeable. And also we can make this kind of battery into the flowable, the structure. So even for the lead acid battery, and if we make a flow, so then it can make more scalable. But for the large scale, the use, as said, so the measure is different from the small scale use we use in the portable electronics. So the safety and the cost is more important than the metric. And in other words, when you choose the material, when you look at the periodical table, at a very critical point, we need to use the material, like some people said, we need to use a dirt cheap material. The dirt cheap. And best said, we just use the dirt as the better material for the large scale use. So then you look at the periodic table. I don't know what the material they're going to be used, but what we know what we need, right? But eventually, what do we need? We need to go back to the fundamentals and with fresh ideas. But in any case, we are from MSE, and no matter what the better technology went out, we were based on the material. Not only for the material science and also for the material engineering, for the processing, especially for the large scale. So the processing or the engineering will become the more important, will play the more important role in the future. Okay, with that, I want to finish my talk. Thanks, for the nearly 2 hours, the really long time. And if you have any other questions, we can have a short discussion.
Oh, thank you, Professor Qing Wang, for the amazing lecture. I think you really cover all the important topics in the energy area, like storage, conversion, even hydrogen production. So that's really, really inspiring. Okay, so students, if you have any questions, you can type in the chat box, or you can speak up by yourself. Maybe I can ask a question first. So I'm curious about the safety aspects of those flow like storage system, because we know the lithium-ion battery, the portable ones, they really suffers from the fire, right? And in the flow system, it seems they are not really portable. So how about the safety issues in those systems?
Okay, as you said, so the lithium battery, the main concern, one is the safety, the other is the availability of material in the long run. Because we are talking about the megawatt, gigawatt, even terawatt use. And for the flow battery, as you said, it's no real deployment so far. Also, the vanadium flow battery has been demonstrated in the 100 megawatt level. It's not in a commercial stage. It's mainly because of cost. For the safety, is not the real concern at the moment. If you look at the chemistry we use in a different system, because the safety is the first thing we need to look at. So that's why they're mostly, if not all, they use a water-based electrolyte. So that's something different from the lithium battery. For the lithium battery, we know the main issues are somewhat run away. They have the interface, the issue they caused by the decomposition of the electrolyte, the general heat, all the things that happen. But for the flow battery, there's no such the problem. But as other the issues, it is said, most of the system we studied are not thermodynamically stable. Although thermodynamic is the first thing we need to consider, but actually when the people choose a material, nearly all the material are not thermodynamically stable. Like lead acid battery is 2 volts, obviously beyond the splitting weight of water, right? Just 1.3 volts. I mean, obviously you have decomposition of water. It's the same for the vanadium flow battery. Vanadium, the flow battery, is mainly on the negative side. The negative side is the reaction of vanadium. If you look at the potential, it's minus 0.25 volt versus NHE. We know the hydrogen formation is 0 volt, right? And this potential is already more negative than hydrogen formation. That means the thermodynamically, so this redox when got to reduce on the electrode, so the hydrogen will be formed already. So to reduce the hydrogen formation, when the hydrogen become a hazard, the safety hazard for the use, we don't want hydrogen and may catch fire and may have explosion, right? So we should try to get rid of hydrogen formation. For example, by mod the electrode, so they can suppress the hydrogen formation. And as the safety concern, if still for the vanadium problem, because the high concentration of acid, and if and also the leakage problem, because the vanadium, the 5, vanadium 5, that's a bit toxic. And if because we are talking about the 1,000 liters or even more, the vanadium electrolyte solution, you got the leak to the environment. So that means there's a hazard from it. But as I said, there's no real deployment. I think people sooner or later they will face such the problem. But compared with the lithium phosphate, I mean, intrinsically, it's safer.
I see.
Okay.
Great, thank you. Oh, and actually, I'm getting some requests from students whether they can rewatch this video. So as I mentioned in the beginning of this session, we're gonna upload the recording of this lecture. So you can maybe watch later, like repeatedly if you want. So are there any other questions? I think students may have some questions or ideas after they
you can always
watch
write to me.
Yeah. Yeah. So I will appreciate if you can answer questions later, like even after
Sure.
the session.
Yeah, you just write to me. I think maybe I write my email address here, just my name, QING. Sorry, I didn't put my email address. That one, AUS EDU SG. Okay, just my name, with the US. Or you can find my name from the website.